Thank you. Thank you very much for inviting me to talk. I'm from SRON, the Netherlands Institute for Space Research in the Netherlands, and we do research from space. And I want to talk to you about our first struggles in the last years to introduce open data management in our institute in SRON, and how we approached it. And in the end of the talk, I will talk a bit about an open data template to help our researchers make reproduction packages for their papers and make their research more reproducible in that sense. We are not doing this for a long time already. So as Daniel said in the previous presentation, we are doing small steps, hopefully in the right direction. And I want to show you a bit what we are doing, which steps we have taken already, and where we want to go and see where we get. But first, let me show you a bit what our institute is doing and what type of data that we have, also to give you an idea what our challenges are in terms of open data and what is already done. Our institute is actually quite unique in the sense that we have several types of expertises in the institute. One of our main missions is to develop a pioneering technology and actually sensor research to make advanced instruments to use in space. So we built cameras, machinery to detect light in space, and try to get new scientific results from it. So we pursue them in fundamental astrophysics, so looking at the stars. We also look at the Earth and at possible other Earths also in the universe. So we have astrophysics, Earth science, and exoplanets actually. And on this slide, you see a couple of examples of missions that we are involved in. And you see that they are from familiar names, perhaps, NASA, the American Space Research Organization, ESA, and also the Japanese Space Organization we have projects with to do this. So a couple of examples, what kind of things do we do? We have, for example, developed an instrument for an Earth observation satellite called Tropomi, which is now in orbit for a couple of years now. And this instrument is designed to detect trace gases in our atmosphere, and especially the ones that we have a problem with. For example, methane is a molecule that is a greenhouse gas and is important for climate change. And we want to see where methane is released into the atmosphere. And the problem is, how do you make a small instrument that fits on a satellite that can really, in large detail, measure methane in the atmosphere? And we have created a grating, so a kind of spectrometer, and that you see in the lower right. You see a nice little piece of glass with kind of rainbow colors on it. That is the core element in the instrument that separates the white light from the sun into separate colors. And with that, we can, I will show you in the next slide, we can measure the methane. And what you see here is a publication that we had last year with collaborators to show that in Texas, where they have a large oil industry, you see higher concentrations of methane, and actually you can associate them with specific oil fields. So we can now measure per oil field how much methane is released in the atmosphere, which of course is a good thing to battle climate change and make people aware that their activities are harmful for our world. So how does this work? How do we get these data? Well, what you see here is on the top, kind of how the satellite flies over the Earth it sees a small band below the satellite of the Earth, with its well, small. It's 7 kilometers thick and about 2,500 kilometers wide. And for each resolution element, you want to have what we call a spectrum. That's how you divide this light into several wavelengths. And this is what it looks like. What you actually measure is the bottom plot. That's the black line there with all these blips on it is the spectrum that we measure. And all these little dips belong to several molecules that are in the atmosphere. So there's the molecule, water molecule, H2O in green, methane in blue, and carbon monoxide in red. So these molecules we can measure for each resolution element on the Earth. And with this, we can make maps. So to show you which kind of things we can do in our neighborhood, this is a map from a previous satellite, OMI on the left, where you see a part of the Netherlands, Belgium, France, and Western Germany. And on the left image, you see some enhancements, which are actually pollutions with NO2, which is also a pollution gas. And on the right side, you see the new satellites, Tropomi, which have a much higher resolution, where you see Paris kind of have a plume of pollution coming from there. And also in Western Germany, the Ruhr area, where a lot of NO2 is being emitted. So with these new methods, we can really pinpoint where the pollution comes from. And of course, this is very important data, also politically, because we want to show which areas produce more pollution and how do we want to battle this. So for our community as a large, it's important that these data are accessible and open. And luckily, these satellites are operated by ESA. There are some measures in place that these data are being open, but still on the level of publications, we still have issues to see, are our publications really reproducible? Can we make these maps so reproducible that we can check whether they make sense or not? This is one example in Earth observation. And our second big topic is astrophysics. And this is a picture that you kind of associated with astrophysics research. A lot of beautiful images with stars and galaxies. And these galaxies themselves contain billions of stars. So a huge universe to discover. And what we do here is not actually look into the universe into visible light, which is this picture, but we have a whole department looking at the universe actually in X-rays. And if you look at such an image here with galaxies, and then you don't really notice that there's a lot more around actually. You see a black background suggesting that there's nothing in between the stars. But if you look in X-rays, you actually see that there's a really big hot cloud there. The purple image in the background is from the Chandra Observatory, and we can image the sky in X-rays. And to compare, I put the optical image in the lower left corner, and this is about the same scale. So this such a galaxy that you see in the lower left, such an orange blob of stars, is about 100,000 light years across, which is already huge to our minds. But you see that this cloud of gas in the background is even larger. It's millions of light years across, and it's actually one big gas cloud. And if you look carefully, then in the center of it, so here around, you see these dark areas in the picture. And these dark areas are actually bubbles of even hotter gas that are rising to the outer parts. So these bubbles are really gigantic. And in the center here, in the square, there's a giant black hole, and matter is kind of flowing around this black hole and ejecting material at really large speeds into the surroundings, which is called a jet. And these jets are actually blowing these bubbles. So it's really an exciting area of research where you see how black holes actually shape their environment. So how do we want to study those? Well, we are actually preparing a new satellite for that, which is called the Athena Observatory, which is an ESA mission to be launched in 2030. And what you get is the following. If you make an image, here you see that in an image you of course have pixels, and for each pixel you can get a spectrum and analyze what the gas is doing. You can see the composition of the gas, but you can also measure the velocities that are there. And of course, if you want to study the bubbles, you want to see what the velocities are there. These astronomical observatories, actually in terms of open data, they are already pretty far. All observations by most of the astronomical observatories, the raw data already public. They are in open archives. You can download observations and observational data for free. There's good metadata with them. They're in file formats that are easily opened. There are standard file formats for that. But then for us, the challenge is, like, if you study such an object, you want to examine very different things. Some people want to look at the composition of a particular area in this image. Some people want to study the velocity. Some people want to study the outer parts. And how do you make the selections? How do you select your data? How do you analyze the data? From the raw data, there are very many paths to get to your scientific result. So although the first part, the raw data, is open, the second part is still a bit of a challenge for us. And to see what are we developing actually for this satellite. Of course, we are interested from a scientific point of view, from an astronomy point of view, what is happening in this object. But we are actually also developing the camera to do this thing, also within SRON. This is a prototype of a camera. You see here a number of pixels. It's about 1,000 pixel array, so about 40 by 40, I think. And this is a very special camera. This is not something that you have in your own camera at home, but this camera needs to be cooled to nearly the 0 point, minus 270 degrees Celsius, really cold. And that's because it uses a very special physical mechanism called superconductivity to measure very precisely the energy of a photon. Oh, I'm sorry, it's going to the next slide that I didn't want. Okay. So you have this pixel that measures the light, and you keep it very cool. And the thing is, if you put it in a very low temperature, the resistance of this block down here is kind of zero. The current can go through it very easily. But then if an X-ray hits, it warms up a little, and then here the resistance goes up. And by measuring the resistance, it's much easier electronically. You measure a photon coming in. And this is something that we're now testing in our laboratory. So we also have laboratory data where these data are generated and also needs to be processed and published in the end. So these are the type of data that we have, the types of things we do. And from about 2 years ago, from 2018 to 2019, our funding agency, the Dutch Organization for Scientific Research, which is a very large science funding agency in the Netherlands, actually put in their strategy to move the Dutch research towards open science. So since SRON is an institute part of this organization, we were also encouraged to start looking into how to make our research more reproducible. One of the main aspects of this is, of course, open data. So easy access to publicly funded research. We want to accelerate the science by sharing the tools and knowledge. Actually, a lot of things that you heard in the previous presentation as well. Tried to solve a part of this reproducibility crisis, and therefore we need to help our researchers to get their papers and get their results more reproducible. Another side step of that is that our NWO organization is also one of the drivers of Plan S to make journal papers better open access. That's the second route that we will not discuss in this presentation, but it's also the Netherlands is at the forefront in that respect. So how are we going to approach that? Because as you saw, we have quite a lot of disciplines within our institute. So both from the science side, we analyze data from satellites, and these satellites are usually operated by big space agencies, so ESA, NASA, JAXA. And actually that makes it partly easier for us. So as I said, within these agencies, has been already decades of experience publishing observations from satellites and data sets to the outside world in very easily readable formats. So that's something that's easy for us. So we can say, okay, we downloaded our data from this archive, and from that we derived certain results. That's one aspect. Then we have data from our own experiments. So on the right, you see a picture of me pretending to work on one of the instruments. I'm not an expert of this, but someone wants to make a photo with that. But these experiments generate a lot of data, and we need to find a way to make them public and make them also open. Because before, when I started this, when we started this in the institute, they used a kind of our own file format, but eventually we convinced them to use an open file format like HDF5 to put the data files in, so that other people can also download the data and see what's in there. Then the third part of data that we identified are the derived data for papers that researchers have in their papers. So those are the images, the spectra, the model comparisons with the data, the figures, etc. And this is a part that was really missing in our part, that was not open. People just generally just published a paper without the underlying data. So that's something that we need to figure out, like how do we format these data? How do we document them for people of the outside to be able to reproduce our results? So that's what I will discuss in the remainder of this presentation. So when we started this, our first idea was like, well, what should be in there in the reproduction package? We were really starting at zero a couple of years ago, and I think a very helpful question to ask a researcher is, imagine that you would have a student who needs to reproduce your result. What would you give that student? What does the student need? And that is a very a question that researchers could use to imagine what they could put in this to this reproduction package. So that could be links to the raw data, to the science archives of ESA and NASA. That could be scripts that derive the products from the raw data. So you get a raw data file from the observation, but then you use some software to derive a spectrum or an image, and these could be very helpful for someone else to reproduce what you did. Other analysis scripts, usually when you have such a data file, you want to compare them with models to actually derive physical properties from these data, from these spectra, from the images. So that you need to include somehow results tables, scripts to recreate figures. This is kind of the list that we identified, and of course, you want to have some README files explaining how to run these files in the end. So this is a list of doing things, but then we had a certain challenges, like how do you make that kind of a singular approach, because we have many different researchers in the house. People use different programming languages. The data sets are also different, for example, between astronomy and earth science. Many researchers don't want to spend a lot of time on it, so you need to kind of make it easy for them. And also, researchers tend to be a bit stubborn. They don't like to change their work unless there is a really good reason to do it. So how do you do that? Try to make it easy. Try to teach them a couple of new things. For example, version control, using GitHub for scripts, or in-house we have GitLab, which is very similar. That helps researchers to familiarize themselves with some very easy tools to make their software reproducible step by step. So we have a couple of data stewards in the institute that help researchers with the open data issues, to how to structure their data and software. We have some data and software training that we give our researchers, and to guide them with a reproduction package, I made a very simple template that guides researchers to a kind of a directory structure. Okay, what types of data do I need to put in my reproduction package, and where, and how do I document that? We have made a very simple template for that to help our researchers to do that. So what's in there is kind of embarrassingly simple. Have a kind of data directory where you put the derived data products and analysis scripts. Of course, in the optimal case, that they work from there directly from the data directory, but of course that depends also on your software dependencies, but that's another discussion. You put those there, and we have a folder called figures, which is per figure a folder which corresponds to the figures in the article, in the publication, so that you structure those nicely, so that you can find back, okay, for figure 1 the figures are created in that folder. And in the end, if you have Jupyter notebooks, which are quite popular these days, not everybody uses them, but that's why they are optional. If you have notebooks that are helpful, you can put them either in the notebook section, or if they better fit in the data or figures, that's also possible. It's just a bit of see with the researcher where these fit best. Then on the top level, you have a README file in Markdown format that scientists can use to explain what is in the data file, which raw data that we use, links to the data archive can be in there. The software requirements that you would need could be described in there. And this README file would kind of show if we upload such a reproduction package to the Zenodo, it would kind of be the first page on Zenodo that you see. That would be immediately the explanation for the entire package. So this is a very simple structure, and of course there's things to be improved. Also in these directory structures, we have also deeper some README files of how to access the data, how to run the scripts, etc. And some guidelines in the README, what scientists can put in there. So this gives a basic idea for a researcher. Okay, how do I structure such a reproduction package, and provides us with the first steps of actually creating these. Although these are not perfect yet, this is the first step that we took, and we can gradually improve it as we learn how to do things better. So this is what a README file in Markdown looks if you render it. So this is just a very simple the template version. So you have some sections about what software do you need, what do you need for the data, for example, what does the package contain, are there Jupyter notebooks, what are the figures, etc. So what is the advantage here for this way of working? I think it has a very high flexibility for our researchers to for a very different way they work. You can there's no software in there, in the template, so you can put in basically anything you want. On the other side, that may also be a disadvantage if you want to come to some standard in the end, but I don't think we are there yet. But for now, I think that's the good aspect of it. We have some guidance inside the template for researchers to guide them what to put into the package. Actually, we put this also now on GitHub, so you can load this template directly from Git. You can clone it or download it and immediately start creating this directory structure and put it into a file format. So these are, I think, the main advantages. What we may need to do still is to build in some more enforcement, perhaps, or guidelines on how to make your things fair. So and then mostly reusable, make your codes, your scripts of better quality. That's not really enforced in this template, but that we do that in a different way. And here you don't have any kind of built-in inclusion of software dependencies, but this could be solved by, for example, making a Docker image of your software environment, for which you can, it's kind of a small virtual machine where you have the entire environment with all the libraries that the software needs in one tar file or in one package that you can download and run within the Docker environment. So that's from the template side. The template is accompanied by kind of a stepwise a recipe. So first, a researcher can download from the Git the directory structure, then can copy their data, Jupyter notebooks, figures, whatever, into the structure and start writing the READMEs with the guidance in there. Then a very important step, step 6, is show the package to a colleague or supervisor. Also what Daniel suggested in the previous talk, it's very good to show the things that you did to a colleague to get the right questions asked, like, hey, but I cannot run this script, what's going on here? And so you can solve already a couple of problems that you may have in the package by just showing it to someone else. Well, when you've done that, you can compress everything and test it on Zenodo first and do the Zenodo thing and get the DOI in the end. And in the end, get it into your paper with a data availability statement. So I put since I was asked to give this this presentation, I put this open data template also in Zenodo for anyone who's interested to use this. You can download it for free. I put a Creative Commons 0 license on it, so feel free to download, adapt it to your needs if you like. Actually, it's also on GitHub. So if you want to suggest us with improvements or changes, please do. We would be very happy to improve this this template and see how we can improve our workflow here. So recently, one of our colleagues already used this open data template actually independently without asking for help. So this is a reproduction package for a paper in our sensor development department. So people building instruments. And well, this is a quite technical title, which I don't want to bore you with, but these researchers used the template to make a reproduction package for their paper, and it shows that they were actually quite independently able to make a very nice reproduction package here and publish it on Zenodo, which I'm very happy with. So to conclude, we've created actually a very simple template to help researchers create a reproduction package for their paper. So if you are interested in this, it's available on GitHub. You can download it as well from Zenodo. And if you want to help us improve it, you're very welcome. I'm open for many suggestions, and we're learning every step of the way. So this is where I want to stop and answer your questions.